In quantum mechanics, physical information, the exact state of every particle, is perfectly reversible and can never be destroyed. But black holes, the universe's most extreme gravitational engines, appear to pull that indestructible information into an absolute dark void and erase it completely. This debate is central to physics because both opposing rules are derived directly from quantum mechanics and general relativity, the two most precisely tested theories in human history. Yet at the very edge of a black hole, these two frameworks make mutually exclusive claims. They cannot both be true. If we cannot resolve this paradox, it means the foundational laws governing the universe are mathematically inconsistent. The physics we rely on to understand reality is broken at its core. General relativity defines a black hole by its event horizon. Here, the curvature of spacetime becomes so extreme that escape velocity exceeds the speed of light. Relativity dictates this boundary is an absolute trap. Any matter crossing this threshold is permanently sealed away. This is a chart showing gravitational wave strain data from the LIGO observatories. The tight alignment between the numerical relativity predictions and the observed signals proves that Einstein's math accurately predicts the macro behavior of these massive structures. However, instruments like LIGO have a strict limitation. They confirm that black holes exist and merge exactly as predicted, but they cannot retrieve a single data point regarding what happens to the matter inside the horizon. By building a mathematically perfect sealed vault, general relativity sets up the extreme conditions required to test and potentially shatter the strict rules of quantum mechanics. To see the conflict clearly, we have to track a single conceptual object falling directly toward that horizon. From a distant observer's perspective, time dilation warps the event. The object slows, stretches, and freezes, never crossing the boundary. But from the infalling object's own local frame, it crosses the horizon seamlessly, experiencing no physical barrier whatsoever. Relativity requires this physical divergence between reference frames. Both paths are mathematically valid and equally real. General relativity promises a smooth plunge into darkness. Quantum mechanics demands chaotic, perfectly reversible particle collisions. They cannot both be true. Einstein's assumption of an uneventful crossing makes a highly specific, testable promise about the black hole's surface. When we zoom in to the quantum level, that promise triggers a crisis. We need to shift our framework entirely from classical gravity to quantum mechanics, zooming into the microscopic scale precisely at the edge of the event horizon. Here, space is never truly empty. It boils with fluctuating energy where particle-antiparticle pairs briefly pop into existence and annihilate. But when a fluctuation straddles the horizon, one particle is pulled down the gravity well, while the other is ejected outward. This escaping particle is known as Hawking radiation, named after the theoretical physicist who first deduced this exact mechanism. This single escaping particle forces a calculation change. To balance the universe's energy ledger, the outward radiation effectively bleeds a tiny amount of mass away from the black hole itself. This mechanism ensures that black holes are temporary features of the cosmos, slowly leaking their mass back into the vacuum. We can fast forward the timeline to observe the cumulative compounding effect of this radiation over trillions of years. As the black hole emits radiation, it steadily shrinks in size and mass. Eventually, we arrive at the extreme endpoint. The black hole completely evaporates and vanishes, leaving only a vast cloud of scattered radiation. This forces the paradox-defining question. Does that escaping cloud of radiation contain the exact quantum information of the stars, planets, and matter that originally fell into the black hole? According to Hawking's original calculations, the answer is no. This radiation is entirely random thermal noise. It carries zero structural information about the original infalling matter. If the black hole no longer exists, and the radiation contains no data, the universe has permanently deleted information. That breaks the bedrock law of quantum mechanics and leaves physics in a state of logical crisis. Modern theoretical physicists are actively attempting to solve this crisis without abandoning the known laws of the universe. The first major hypothesis assumes the quantum information was never actually destroyed, but rather impossibly scrambled beyond recognition. One hypothesis suggests the information survives, encrypted in hypercomplex correlations hidden deep within the outgoing stream of Hawking radiation. The pragmatic flaw in this model is staggering. These patterns would be so phenomenally chaotic and subtle that it would be physically impossible for any observer or instrument to ever read or reconstruct them. While this encryption model technically saves the mathematics of quantum conservation, it leaves the actual mechanics of how that information is recovered a total mystery. This forces physicists to look for more radical structural answers. A second hypothesis solves the information deficit by completely redefining the fundamental nature of space itself. This is the holographic principle, the concept that all the complex three-dimensional information inside a volume of space is completely and mathematically described by two-dimensional data stored on its outer surface. Applied to a black hole, this means the vast, deep interior doesn't hold the data. Instead, the quantum state of everything that fell in is smeared across the 2D surface of the event horizon. If the holographic principle applies to every volume of space, it implies that the three-dimensional depth we experience daily is a secondary effect of surface data. If true, the three-dimensional universe we experience daily might literally be a holographic projection generated from a distant two-dimensional boundary. To save the conservation of information, a major branch of theoretical physics is entirely willing to sacrifice the fundamental reality of three-dimensional depth. A third competing model bypasses space entirely and attacks general relativity's core assumptions directly, the firewall hypothesis. This model argues that to preserve the quantum data at the horizon, the boundary cannot be an empty, uneventful crossing. It must physically manifest as a highly energetic barrier. This requires a violent firewall. Any incoming matter is instantly incinerated upon touching the boundary, abruptly halting its inward journey. This perfectly preserves quantum mechanics, but it deliberately breaks Einstein's foundational rule of an uneventful crossing. This leaves physics in a deadlocked state. We have three distinct models: hidden correlations, holograms, and firewalls, and each one saves a vital part of physics only by violently breaking another. Until humanity achieves a unified theory of quantum gravity, this paradox remains an open, bleeding edge of science. It is a pure logical crisis that no current observational telescope can solve. Solving this contradiction provides the direct path to a unified theory of quantum gravity, redefining spacetime and the survival of information in the cosmos.